Hello, analysts. So, those of you who check the web page compulsively or have a subscription to the YouTube will notice that this lecture has already been posted once before this particular posting. The reason that I'm reposting it is twofold. One, the video quality on the uploaded video was garbage. I'm hoping that the way that I'm recording this one will fix this. The second reason is I'm going to try to record, instead of full lectures, I'm going to try to break them into pieces. So you can watch one piece, digest it, and then come back and watch the other one. And this lecture is naturally broken into two pieces. An application piece and a proof piece. So today I'm going to, in this particular video, I'm going to introduce the Cauchy criterion and tell you what it says by using it to do something. That is a perfectly okay noise. The cats are doing something. So right now, let's motivate the Cauchy criterion, say what it says. We have a sufficient condition. We have a sufficient condition right now that tells us what it means for a sequence to converge without having us to guess a limit for the sequence. And this is useful if you can check that a sequence satisfies the monotone convergence theorem. The monotone convergence theorem. Then you'll know that it converges without having to know what the limit is before you show that it converges. And that's useful, because once you know that a thing converges, you can do something to prove what the limit has to be. Let's recall the statement. So the statement of the monotone convergence theorem is as follows. If a sequence is monotone and bounded, then it converges. And we use that sequence to show that theorem to show that certain sequences do converge, and we prove that they converge without needing to know what the limit should be in advance. Now, something to note, this is an if something happens, then the sequence converges. So it's a sufficient condition for convergence, but it's not a necessary condition for convergence. You might check that a sequence fails to be monotone and bounded. That doesn't mean that it diverges. So, what I'm going to develop today is an if and only if theorem, a theorem which will be equivalent to convergence. A sequence, A sub n, is called Cauchy if, for every epsilon bigger than 0, there exists a big N such that if little m is bigger than big N, and little n is bigger than big N, then A sub n minus A sub m is less than epsilon. So let me write that in all just the symbology off to the right. So A sub n is Cauchy means for all epsilon bigger than 0, there exists some choice of big N. So notice, this big N can depend on epsilon, such that for all little m bigger than big N, and for all little n bigger than big N, absolute value of A sub n minus A sub m less than epsilon. So let's try to parse this out. So at its face, this looks a little bit like the definition of convergence. If you want to be like sloppy, you would say, oh, this means that like A sub n converges to A sub m. But it doesn't say that, because this A sub m is not fixed. As m gets bigger, that A sub m is going to have to change as well. So let's read what it does say. So the way you should read this, for all epsilon bigger than 0. So that's no matter what error bound, no matter how tight a spread you want, no matter how small a number you pick, no matter what tiny error you want this estimate to have, there exists some threshold value, big N. There exists some big number so that once you're past that number, something will happen, such that if you only consider indexes which are past that threshold value, so if you only look past that threshold value, then the difference between the two terms of the sequence is less than epsilon. So informally what this means is as the index in the sequence gets really, really big, the terms of the sequence are all clustering really close to each other. That's what it means to be Cauchy. The terms of the sequence get close to each other. And the idea of what completeness is supposed to mean, like the real numbers are a complete ordered field, is that if a bunch of things look like they're getting close to something, there should actually be something there. So there's a motivation for the Cauchy. There's the statement of the Cauchy condition. That's a definition, not a theorem. Here's the theorem. The Cauchy criterion for convergence. A sequence is convergent if and only if it is Cauchy. So that's really powerful. To show a sequence is Cauchy, you don't need to have this guess about what the limit should be. You're not showing it's Cauchy to something. You're just showing that the thing is Cauchy. Another thing to notice is this is an if and only if. So if you fail to show a sequence is Cauchy, that doesn't necessarily mean it isn't Cauchy. That just means you couldn't do it. But if you can show a sequence fails to be Cauchy, then you know that sequence diverges. So you don't lose any information by trying to check for Cauchiness instead of convergence. Well, you don't know what the limit is, but generally you don't anyway. So let's make an application. Here's a sequence. For any natural number n, I will define S sub n to be the sum from k equals 0 up to n of things that look like negative 1 to the k divided by 2 to the k plus 1. So if you, in case you are less familiar with summation notation, which maybe you feel a little bit uncomfortable, so the way to read that is you're going to run over all those traces of k. You'll plug those k's into this formula. You'll take all the traces of k from 0 to n, you'll plug those k's into this formula, and you'll see what you get. You plug in k equals 0, you get negative 1 to the 0 is 1 on top, 2 to the 0 is 1 plus 1, so 2 on the bottom. K equals 1, you'll get negative a third. K equals 2, you'll get negative 1 squared, so 1 divided by 4 plus 1, and so on. You'll just keep on going. There's the generic kth term, and this formula stops at the nth term. Here's the claim. This sequence is Cauchy. Maybe I'll even add a little interjection at the end. And so converges. So right, every Cauchy sequence converges. Cauchy if and only if convergent. So I want to show that this sucker is Cauchy. The definition of Cauchiness, it's about time for me to start teaching a class. The definition of what it means to be Cauchy is right here. For every epsilon, there exists a big N such that for little m and little n bigger than big N, the absolute value of a sub n minus a sub m is less than epsilon. So I know how the proof should go. I should start by considering any choice of epsilon. Then I need to come up with a choice of big N. Since I have a formula for this sequence, I might even get a formula for the choice of big N. Then I should consider any little m bigger than big N, any little n bigger than big N, and try to show this inequality. There's what I need to do. Depending on how you feel, I encourage you to pause this video, read through the rest of on the next page of the notes. There's a guide for the proof. Try to fill it in. You might not have the exact same proof as I do. There's many ways to prove a thing. Okay, cool. You're back. You already have your proof. I'm going to write down mine. So we'll start by considering any epsilon bigger than 0. Since I have a formula for the sequence, I bet I can get a formula for big N, but I certainly can't get a formula for big N just by guessing. I need to figure out what I need it to do. So I'll fill in this blank once I have the proof done, and then I'll read through the proof to make sure it's a proof. I'll let big N be something that I'll figure out later. Consider any little m and little n bigger than big N. Great, so there's like this much of the setup. Between little m and little n, one of them is bigger than or maybe equal to the other. So let's assume without loss of generality that little n is bigger or equal to little n. Little n is bigger than or equal to little m. Then, well, right, so when I make these things I'm intending to print them out, so I didn't have space for what I want on the rest of this page. This gap is intentionally blank. Then, what happens? The absolute value of S sub n minus S sub m, let's just write it out formula-wise. S sub n is by definition the sum from k equals 0 to n of that formula. The definition of S sub m is the same thing, but with an m instead of an n. And in fact, those of you who feel very comfortable with summation notation will be perfectly fine going on to the next step and seeing that cancellation. But I don't want to assume that, especially since I get zero feedback from you while I give these lectures. Let's expand out each of those using what summation notation means. So this is, I'll color code to make it easier to follow. Let's expand out S sub n. Now remember, n is bigger than m, or equal to m. So that means in the course of writing out this red sum, I'll come to an mth term sometime before I get to an nth term. So I'll reflect that in the way I write. So the sum from k equals 0 to n is, let's see, I know that this will simplify, but for emphasis, there's the 0th term plus the first term and I want to go all the way on to the nth term, but so that I see what cancels, I'm going to stop at the mth and then keep going. Negative 1 to the mth term, to the mth, divided by 2 to the m plus 1. So there's the mth term. Now I need to keep on going until I make it to the nth term. Cool. So there is the sum from k equals 0 to n of negative 1 to the k divided by 2 to the k plus 1. Excuse me. I will now write down the blue piece. I'm really taking advantage of the fact that I have infinite board space right here. Let's write out the blue piece. And I'll put it in parentheses just so I remember that I need to distribute a minus sign. Negative 1 to the 0 over 2 to the 0 plus 1 plus plus, and this one stops after the mth term. Negative 1 to the m divided by 2 to the m plus 1. And let's zoom out just enough so that you can see that full thing. And take a look at this and see if you see anything that cancels. And well, of course you do. You see that all of this term, that's the sum of the first m terms of the sequence. I'm right here subtracting exactly the first m terms of the sequence. Those will cancel. Let's cancel those common terms. So I'll be left with just the middle piece. Absolute value bearers persist. Negative 1 to the power m plus 1 over 2 to the m plus 1 plus 1 plus plus negative 1 to the n divided by 2 to the n plus 1. Now one of the advantages of summation notation is it takes up less space than writing it out with a ... notation, and it's also a little bit more explicit. You need to kind of know that I mean to let those exponents run through all the natural numbers between. So I'll rewrite that in summation notation. That's the same as the sum. K will run from m plus 1 up to n of negative 1 to the k divided by 2 to the k plus 1. Nice. So the sum has simplified some. The sum has simplified a little bit. So if you remember, you proved for a homework assignment a triangle inequality that involved a sum of a bunch of things. You proved it using the triangle inequality for two things and a bit of induction. Let's not reprove it right now, let's just use it. I can move what that says is I can move the absolute value bar to each term of the sum. And what will that do? Well, that will keep the positives and negatives from fighting. So instead of canceling, they'll all stack. So the thing will get bigger. Unless it was already all positive, in which case it will stay the same. So that's less than or equal to the sum from k equals m plus 1 up to n of absolute -1 to the k divided by 2 to the k plus 1. Nice. And now let's just try to simplify it. So -1 to the k is the same as 1, and 2 to the k plus 1 is positive. Maybe I'll write that down too. And 2 to the k plus 1 is bigger than 0. So it's really easy to deal with those absolute value bars. The absolute value bar is going to erase the -1 to the k and replace it with a 1, and that's it. This is the same as the sum from k equals m plus 1 up to n of 1 over 2 to the k, I cat, plus 1. Cool. And at this point, I'm going to kind of put on my Calc 2 brain. Remember things from Calc 2. We won't directly use things from Calc 2 except as motivation, because we haven't proven these things. We will in an optional lecture because of the whole, well, it'll be optional because of the whole COVID-19 thing. Let's just take a look at that. You would want to compare that with the geometric series with just a 2 to the k. You would like to erase that one. Oh, well, I mean, basically we can, right? 2 to the k plus 1 is certainly bigger than just 2. So if I replace the 2 to the k plus 1 with just a 2 to the k, that is strictly less than the sum from k equals m plus 1 up to n of 1 over 2 to the k. To make the next step easier to see for those of you who feel uncomfortable with summation notation, I'll expand it all out. Those of you comfortable with summation notation already see that all of those terms have at least m plus 1 1/2s in them, so you should factor out a 2 to the power m plus 1. That was the alarm for me to let the cats back in, but as you hear, I already have done. So let's expand this out and see how many 1/2s we see in it. So first I'm going to look at k equal to m plus 1. So that's 1 over 2 to the power m plus 1. And then I'll need to run over all of the natural numbers between m plus 1 and n. I don't have enough space to write more terms. So I can definitely factor out a 2 to the m plus 1 out of this term. I can factor out a 1 over 2 to the power m plus 2 out of this term. I don't see an m plus 1 here, but n is bigger than m, so I can, in fact, factor out a piece here. So if I do that factoring, sorry, hopefully by the time I finish recording all of these, I'll be better at doing this. This is exactly the same as 1 over 2 to the power m plus 1. Factor out, pull out, this is exactly 1 over 2 to the m plus 1. So I'll see 1 plus 1/2 plus dot 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 plus that last term. Well, I'm pulling out m plus 1 1/2s. So that'll leave me with n minus m plus 1. Cool. And let's put it back in terms of summation notation. And in that step, I factored out a 1 over 2 to the power m plus 1. So those of you who didn't wind up translating to the world of, well, expanding out the summation notation, not writing the thing down in a formula that looks like this, would have jumped right to here without any walk, and that's just fine. So the whole point of doing this is I have a formula for what the geometric series says. Maybe I'll write it right here. So I encourage you to pause for a second, look up the formula for a geometric sum. Okay, good. You did it, and you're back. The geometric sum formula says that the sum from k equal to 0 up to m, not m, m already has a job. I want to use something that's not, doesn't appear right now, to p of x to the k, for instance, x might be a half, is the same as 1 minus x to the power p plus 1 all over 1 minus x. And there are a half dozen different proofs. You might prove this by induction. You might prove this by multiplying x to the k by 1 minus x and seeing that you get 1 minus x to the p plus 1. Those are maybe the two most obvious proofs that I can think of. So let's use that. By the formula for a geometric sum, well, you better believe it's a geometric sum if you're going to use that. That is a geometric sum with x in a language to the right off screen equal to 1/2. So this is 1/2 to the power m plus 1 times, let's see, so it was 1 minus 1/2 to, well, there's the thing that had the job of p off to the right. So 1 minus 1/2 raised to that number plus 1. So that's n minus m all over 1 minus 1/2. So there's what we get out of the geometric sum formula. And now let's kind of try to motivate. Our goal is to show that this thing is small, right? I want to get this to be less than epsilon. Well, certainly, there's something that's getting small. Right. M is getting big, so 1 over 2 to the m plus 1 is getting small. Let's look at this piece. Think about what it's doing. The denominator looks like it's just 1/2. Okay, well that's fine. That means I guess I'll multiply by 2. The numerator, it's 1 minus something that's getting small. So it's close to 1, and it's, in particular, a little bit less than 1. So let's use that. So let's use the fact that 1/2 to the power n minus m is bigger than 0. So in the numerator, I see 1 minus a positive number. That'll give me that this is less than 1 over 2 to the m plus 1. I'll leave that alone for now because it's a piece that I like. Times 1 over 1/2. Which maybe I'll simplify that a little bit. I think that's 1 over 2 to the m. Ooh, well, both m and n are bigger than big N, so let's use the fact that little m is bigger than big N to conclude that this is less than 1 over 2 to the big N. This should make you happy. As big N gets big, this quantity gets small. And that means that I should be able to go off to the side I should be able to take that and solve for big N. And well, there's the solution, right? You do it. So there's our choice of big N. with that choice of big N, I get that this is equal to 1 over 2 raised to the log base 2, 1 over epsilon. 2 raised to the log base 2, like those two operations cancel, so you end up with 1 over epsilon equal to epsilon. And that is true because big N is equal to log base 2 of 1 over epsilon. And one might object to a little bit of this proof, but I'll give an alternate in a moment. Let's read through this and see if this is actually... Oh, I should write down this at the beginning of the proof. Oh, well, I've shifted things a little bit. That's okay. So it's that big N be the log base 2 of 1 over epsilon. All right, so let's read the proof. Consider any epsilon bigger than 0. Any epsilon n proof should start with that. Consider let n be equal to log base 2 of 1 over epsilon. I haven't told you why. You just have to hope that it'll walk out correctly. Consider any little m and little n bigger than big N. Sorry, when I say like you have to hope that it walks out correctly, if you're just reading this proof, you don't know where that came from. Consider any little m and little n bigger than big N. Sure, that's what you need to do. Let's assume without loss of generality that little n is bigger than or equal to little m. And now let's read the proof. All right, so S sub n minus S sub m. Well, that's equal to, yeah, there's the formula for S sub n and the formula for S sub m. By canceling common terms, you get the sum from k equals m plus 1 to n of that. By the triangle inequality, you can move the absolute value bearers to each term of the sum. You can erase the absolute value bearers. They'll just make everything positive. Because 2 to the k plus 1 is bigger than 2 to the k, erasing that plus 1 will make the denominator smaller and so make the whole thing bigger. So this inequality is correct. And there it is, just expanded out again. You can factor out a 1/2 to the m plus 1 to get this. And now you can use the geometric sum formula to get that this is equal to 1 over 2 to the power m plus 1. That's that, 1 over 2 to the m plus 1. Times. All right, so this stuff is not really part of the proof, is it? By the geometric sum formula, you get this. And, well, that top is certainly less than 1, so let's just replace that with 1. That makes the whole thing bigger. And the denominator is just 1/2, so there you go. That gives you 1 over 2 to the n, which is less than 1 over 2 to the big N, since little m is bigger than big N. The definition of big N is the log base 2 of 1 over epsilon. So only in this last step do you actually see why the choice of big N was made. That simplifies down to epsilon, and you're done. Those of you who object that we haven't proven that there exists a logarithmic function, it's a fair objection to make. Right? Why should the exponential function be 1 to 1? And then why should the inverse to that have any nice properties? Well, here's an alternate strategy. It certainly is true that 2 to the big... let's just do it right here. So you get down here to 1 over 2 to the n. Powers of 2 are certainly bigger than the power itself, since little n is bigger than big N, and 2 to the big N is bigger than or equal to n, as long as n is a natural number. Ooh, nope, that's wrong. Sorry, that's cats again. Let's hold on a second. Okay, the cat appears to be done. So 1 over 2 to the n is certainly less than 1 over n. And well, hey, I'm not going to write out the full proof in this case. Do you think you could figure out how to take this and find a choice of big N that results in that being epsilon? Of course you can. 1 over epsilon would do the trick. That's, if you like, a less efficient choice of big N, but that's okay. Less efficient in that it's a bigger choice of big N than log base 2 of 1 over epsilon. All right, so what does this proof do? Well, we start by considering any epsilon bigger than 0. Then we come up with a big N. Sorry, I'm justifying this. So we've shown that for every epsilon bigger than 0, because we start by considering any epsilon bigger than 0, there exists a big N, namely this or that, such that whenever little m and little n are bigger than big N, s sub n minus s sub m is less than epsilon. Thus, this sequence is Cauchy, and so it has a limit by the Cauchy criterion. Okay, I'm going to stop and post this to YouTube. I will post another video in which I will go through the proof of the Cauchy criterion.